Okay, now we're on our work about differentiation, and we're looking here at the derivative today of two things, of e to the power of x and also log x to the base e, or natural log x. Now this is pretty complicated, guys, so just, really concentrate here. If f of x equals e to the power of x, the derivative is e to the power of x. Okay, that's pretty difficult stuff, isn't it? Okay, not. Obviously, it's pretty straightforward. Okay, the derivative of e to the power of x is e to the power of x. Okay, so if your original function is e to the power of x, Aidan, what's the derivative?
E to the power of x.
Good, we've got that established there. Established, okay. But obviously we're going to get a bit harder than that. And the first one here is y equals e to the power of negative 5x. Now I'll show you how to do this using the chain rule, which we used yesterday, and then there's going to be an obvious shortcut, which we'll do after that. So, here with this one, because we've got y equals e to the power of negative 5x, let's make u equal, so our substitution yesterday, remember, equal to negative 5x. Okay, so then our function, instead of being e to the negative 5x, if we let u equal negative 5x, what does the function become now? E to the power of u. Alright? Remember, when using the chain rule, we've got to find two things. First of all, well, it doesn't matter which order. First of all, I'm going to find dy du, which is the derivative of the new expression. What's the derivative of e to the power of u? E to the power of u. Then, of course, we get the derivative of u, which is du dx. What's the derivative of negative 5x, guys? Negative 5. So yesterday with the chain rule, once we'd found dy du and du dx, what did we do to the two of them? Times them together. So dy dx, sorry this is a bit all over the shop, but limited room. So dy dx now equals negative 5 times the other one, e to the power of u. What's the last thing to do then? Substitute back in. So it equals negative 5 e to the power of negative 5x. Alright, so let's get a red pen going here and circle the question and the answer. Based on one example, guys, see I've circled the question and the answer. Based on one example, only of course, what could be the shortcut here instead of using the chain rule each time? Ben?
Coefficient of x out front.
Yeah, it's a bit more than that. It's the derivative of the index. The derivative of that goes out the front and the index stays the same. The derivative of the index goes out the front and the index stays the same. Let's use that same rule now instead of using the chain rule every time, which is time consuming. Let's use that same rule now on this one. So, dy dx, oh, still in red, doesn't matter. Dy dx equals, so remember that rule I just said? James, what's the derivative of the index there? 2, because the 1 disappears, and we just get 2. E to the power of, the index stays the same. 2x plus 1. Pretty straightforward. Put that down. Let's wait a sec. Okay. All right. It's a bit different. E to the power of x outside of e to the power of x minus 2. What do you think? Expand the brackets. Okay, and that's a really important step. Now, here we go. We haven't done indices for a while. What's e to the x times e to the x? E to the power of 2x. Remember when we've got indices and we're multiplying them, we add them. So x plus x is 2x. So e to the power of 2x. And then we've got minus 2e to the power of x. So times out the bracket, like so. Now to get f dash x, hiccup there. get the derivative, we take the two things separately. All right, so let's start with getting the derivative of e to the power of 2x. So remember, it's the derivative of the index goes out the front, index stays the same. Jaden Brown, what's the derivative of the first bit? 2e to the? Good. Okay, and the second bit, what's the derivative of x? 1 gets multiplied by the negative 2 out the front, so it stays at negative 2. Okay, e to the power of x, so that stays the same. So there's our answer. Now, what we could do there, if we wished, is to factorise that, because 2 is a common factor of both expressions. Now, of course, nothing can be done with the bracket. I hope there's people now thinking, I wonder if you can take 2x away from the x. Okay, they're not like terms, so that's as far as you can go. Next one. Oh, this looks complex. I wonder if it is. What do you think about here? Yes, Annalie?
So you have like e to 2x plus the x minus.
Yes, excellent. Remember that thing the other day, and I gave the example of, I can't remember what I used, but it was something like 7 plus 6 over 2 is the same as 7 on 2 plus 6 on 2. Remember that? So when you see this sort of situation, that's the first thing you should think about, is doing that very thing. So I'll just get rid of that. But we talked about this the other day. So it's going to be e to the power of 2x over e to the power of x. So those two guys there, minus 2e to the negative x over e to the power of x. All right, now we have to tidy that up. We're dividing with indices with the same base. It's e both times. So what are we going to do with the indices when we're dividing, Jess?
Minus
So what's 2x minus x?
x.
So that's e to the power of x for that one. Over here we've got minus 2. Okay, so we've got e to the minus x divided by e to the x. Subtract the indices. What's minus x, or negative x, sorry? Take another x. Negative 2x, so we get e to the negative 2x. Okay, so that's our f of x. Therefore, f dash x, Aidan, derivative of e to the x?
E to the x.
Okay, I'm going to run out of room here. So, next one, let's look at this in isolation. Here it is. Okay, so the rule is that you get the derivative of the index. Jackson, what's the derivative of that index there?
Negative 2.
Negative 2. It pops out the front and gets multiplied by what's already there, which is the negative 2. So we get plus 4. Let's repeat that. Derivative of the index is negative 2 multiplied by the coefficient. Negative 2 is positive 4. And the index stays the same. Let's just run out of room there, but I think try and squeeze it in if I can. Have I made a mistake? Jordan, am I right?
No.
Yep. Okay, hopefully you can read that. So there we go. Okay, another one. Y equals x cubed minus x. Sorry, y equals e to the power of x cubed minus x. So dy dx equals... Okay, what's the derivative of the index? Annalie? 3x squared minus 1. Bracket that. E to the power of. The index stays the same. There we go. That was an easy one. Right with that?
I think so. Yep.
Here's the rule that sort of summarises what I've been saying verbally. That is, with these questions, if your function is exponential like that, e to the power of another function, the derivative is the derivative of the index, g dash x, so the index is g of x, multiplied by e to that same index. That's the rule that sums up what I've been saying now, the shortcut. I wanted to use the chain rule first up just to show you once again it can be used, but I think most of you are pretty comfortable with using that little shortcut rule. Just repeating it. Original function e to the power of another function. The derivative is the derivative of the index multiplied by e to the same index. Let's do something. Okay, here we go. Here's the first example. Y equals log 7x to the base e. So we're going to use the chain rule again. So I'm going to let u equal 7x. Therefore, du... Actually, no. I'll go back a step before we do that. So the expression now becomes y equals log u to the base e. Now that generates for us two expressions. Du dx. Derivative of 7x, James? 7. And that also generates dy du. It's a terrible y. Dy du. And we just, on the previous slide, talked about that log x to the base e, the derivative is 1 over x. So what's the derivative of log u to the base e? 1 over u. Then, using the chain rule, we multiply those two results together. 7 times 1 over u equals 7 over u equals 7 over 7x, which equals what? 1 over x. 7's cancel. 1 over x.
So
Yes, I can hear the so statements. What's your so statement, Aiden?
Even if there's a coefficient of x, it's still just 1 on x.
Yeah,
Good one.
yeah,
Right.
yeah. I'm glad you investigated that. So if the question had been log 370x to the base e, same situation would have
So
developed.
any log 1 is just 1 over x.
Correct.
Then what's the point in?
I wanted you to come to that conclusion rather than me just telling you.
1 over x.
Let's do this one. Let's do this one and see what we get here. All right. So substitution will be let u equal 3x minus 4. So y will now equal 2 log u to the base e. Meaning that du dx will equal what? Chelsea, what's the derivative of 3x minus 4? 3. You're looking a bit too deeply into that. Was all right. 2. Then we've got dy du equals. What do you think that is? We've got 2 times log u to the base e. Liam? What do you think the derivative of that guy there is? 2 over u. That's right. Just to break that up. So the derivative of that is 1 over u multiplied by 2 is 2 over u. Dy dx will be those two multiplied together, which will be 3 times 2 over u, will be 6 over u, be 6 over 3x minus 4. Alrighty. Who sees a shortcut?
Would you
Yep.
simplify that by 2 at the end of it? Divide everything by 2.
No, because 2 doesn't go into 3. Remember, to simplify there, 2 would have to go into 6, 4 and 3.
What about,
Yep, please, you said what about? Yep.
I think I'm going to you put what's in the brackets on the bottom,
Yes.
and then you times what's in front of the log by the derivative of x.
Yes. Fantastic. Look at this. Look at this. Here it is. The shortcut rule, copy this down. The shortcut rule is the derivative of the bracket over the bracket. And of course, the derivative on the top gets multiplied by a number if it's already there. Okay, so if there was a 3 there, don't write this in your notes, but if there was a 3 there, that 3 would also go there. So Chelsea, you're dead right. You get the derivative of the bracket over the bracket. Pretty simple rule to use. Bearing in mind that if there's a coefficient in front of the log expression, that has to be included. Who wrote the 3 in? Well, it's gone now. Neat, wasn't it? Is that all right? Got that down? Got that down, Jaden?
Yeah.
All good? Both Jadens? Okay, now we can whip through a couple of examples now. Here's one. Log x squared plus 4x minus 4. So derivative equals derivative of bracket 2x plus 4 over bracket x squared, it's a bad squared, x squared plus 4x minus 1. Good work, easy. Got that? We're going too fast? Good point, I forgot about that. Well done, Ben. Good practice to factorise any brackets that can be factorised. Well done. So there we go, we factorise the top.
Is there any way to get the bottom?
If the bottom could be factorised, we should, but it can't be. There's no factors of -1 that give 4. So we'll leave it as it is. No, good point. All right, next one. Okay, now, this one's a bit of a tricky extra step. Remember, we had a rule. Actually, I'll just get rid of the A for a second. How can that, this is a digression, but it's important, it can be in your notes if you wish. How can that also be written? Who remembers back to our log rules? Yes, Matt?
The end goes out the front.
The n goes out the front, so it can become with that. All right, so with that in mind, the question becomes, the index pops out the front, 2 log, all that stuff to the base e. Okay, so I'll just get rid of this little reminder now. All right, so now we apply the rule to y dx equals 2 multiplied by derivative of bracket, which is 2x plus 5. I think we'll do a bit better than that. We'll do a bracket there instead of a times sign. Okay, over the bracket. Just do a quick check for common factors. That can't be cancelled, can't be factorised, neither can that. So there's our answer.
Why don't you times the 2 by the 2x and then
It's good to have it in factorised form. Okay. There's our rule, so we're done.